that the Twin Towers?
If you guys remember from our previous class, we started to discuss the important concept of stress. So we define stress as the intensity of force. So the force on every section could be a normal force or a shear force. So the intensity of normal force is called normal stress. We show it with the Greek letter sigma. The intensity of shear force is shear stress. We show it with the Greek letter of tau. So as you can see, both of these two equations that I have shown over here, these are equations including limits. So it looks like that we can only calculate the stress if we know how the shear force and how the normal force are changing throughout the cross section, throughout the area. If we have that variation, if we have that equation, we can calculate these limits. But this is an engineering class. We would like to, you're wondering if there are some engineering elements in real life that we can calculate these stresses without going through these kind of, complex equations of variation of stress. So let's think of, so here's what we're going to do today. We would like to actually calculate the stresses. However, we're going to start calculation of stresses for the first structural element that we would like to discuss in this class. And that's a prismatic bar, the simplest type of element that you can imagine. You guys work with these kind of elements in your class of statics. Whenever you had a truss system, a two-dimensional truss, three-dimensional truss. So these are actually like two force members. The two force members are the members that are either subjected to tension or compression. So if we have a longitudinal element that we can qualify it as a prismatic bar. So why am I calling this prismatic bar? Because I would like to emphasize that the cross section does not change throughout the length of the member. So if I have a member like that, which is a straight element, the length is actually higher than the dimensions of the cross section, and I actually apply either compression or tension to that element, I can calculate, first of all, I can identify what type of stress I have in every cross section. What is your opinion? Let's start with this question. What type of stress do we have on every cross section for a member like this, for a member that is subjected to either tension or compression? And by cross section, I mean a section that is perpendicular to the lineal axis of load. What type of stress do we have? Do we have normal stress or shear stress? The answer is kind of obvious. So its load is perpendicular to the cross section, so that's a normal force. It means that on every cross section, we should have normal stress. We should have normal stress. But the question is that, are we able to calculate that normal stress or not? So our equation, let's just go back to the equation for normal stress. So this is how the normal stress can be calculated. So I mentioned that, if we have the function, if we know how n varies with respect to the location of area, we can actually calculate this limit. But how about a case where the stresses are uniformly distributed across the cross section? In that case, we can actually easily divide the force by the area because the value of the normal stress at every location is equal to the average normal stress. So, what we would like to say in our today's class is that for these type of prismatic bars, if these conditions are satisfied, we can confidently say that the normal stress is distributed uniformly, and we can easily calculate it. So let's go through these assumptions. So what are these conditions? Number one, if the bar is prismatic. So in the other words, if we have a constant cross section throughout the length. If the material is homogeneous, so what is the meaning of homogeneous over here? It means that the properties of that material does not change from one point to the other point. So we have a uniform distribution of material properties. So we can say that properties are the same. We have not discussed the material properties yet in this class, but let's actually define this this term over here. So properties are the same at any point. And also the material is isotropic. So what is the meaning of isotropic? It means that the properties in every direction is the same. For example, under tension and compression, it behaves the same. It's not, doesn't behave different. So properties are the same. Let me just write that definition here. Properties are the same at any direction. This fourth assumption is even much more important. We would like, this is an important assumption for us in this class. The member is axially loaded through centroid. The member is axially loaded through centroid. So it means that this point of action of the load here, or here, or here, or here, these are exactly the location of centroid of the cross section. So why this assumption is important is because if we have eccentricity, if the force is not passing through the centroid, we do not have only axial force in every cross section. We're going to have a combination of axial force and bending moment. We're going to discuss this later in this class, but if you write the equilibrium equations that you learn from statics, you can investigate them. So it means that, this is what we mean here, it means that the member is not bent, is not subjected to bending. So I'm going to say not bending. And also this fifth assumption is conceptually important for us. We are not near the ends of the bar. Why there is such an assumption? What is the meaning of this assumption? It means that we are actually far from the two ends of the bar. For example, we are looking at this cross section. So what will happen if we are close to the points of the end points? We're not going to have a uniform distribution of stresses. We're going to have a phenomenon that we call it stress concentration. So when we have stress concentration, this equation that I'm going to actually just tell you momentarily, that equation is not going to be valid. So I'm going to say that we do not have any stress concentration, or in the other words, stress as enough distance to level out. This is the meaning of this fifth assumption, or fifth condition. So how about if we have a member that satisfies all these conditions? Then we can say at every cross section, at every section that is perpendicular to the line of axis of the member, that is perpendicular to the line of axis of the force, we're going to have a uniform distribution of stresses. For example, if I make it cut over here and look at the bottom part, so I'm going to have a force F that is applied to this member, that is applied at the centroid, and the stresses are distributed uniformly. The intensity of stress is going to be the same across the cross sections and every point on that cross section. In the other words, in order to calculate the sigma for normal stress, I can say that that normal stress is going to be equal to the average normal stress, or in the other words, it's simply equal to F, or force divided by the area of the cross section. This is the simplest form of equation that we can think of for calculation of stress. It would be great if we can always, especially You know, if you think about, you know, the mechanics of the systems from design point of view, this is the ideal distribution of stresses. We have, you know, it's the same contribution from all points of material in supporting the load. That's a great type of distribution that we like. And we can, the good news is that we can simply calculate that stress. Yes? Average. So it's a sigma sub ADE, which is sigma average normal stress. So thanks for your question. Please ask these are simple questions, but it is important that we make it absolutely clear. So now it's time to actually use that equation. Where can you use this equation? Let's take a look at this example over here. We're going to actually use this example several times later for calculation of different quantities. So what kind of system do we have? As you can see, we have two bars that are connected together. Well, let me just make some of these letters clear. So we have clearly a pin support over here. This is point A. We have, you know, the bar AB is connected to the bar BC through this joint over here. And A is a pin support, C is a pin support. The bar BC is subjected to a lateral force or transverse force of 2,000 Newton. And this is 60 degrees, this is 2 meter, this is 2 meter, and this is 3 meter. These are the information on this system. So, the problem is asking, determine the average normal stress in member AB. And the diameter of that member is 30 millimeters. So it means that we have AB has a circular cross section. So, how should I answer that question? How should I answer to this question? What should I do first? You have the equation, you have the information about the area, you can simply calculate the area of member AB. So, how can I calculate the normal stress? I need to first calculate, yes, the force, exactly. We need to calculate the force, the internal force in member AB. So, are we able to do that? Why? How? Yes.
The reaction force of A first.
So we need to identify whether this system is statically determinate or indeterminate. If it is determinate, we can use our knowledge of statics. We can write equilibrium equation. We can draw a correct free body diagram. We can write equilibrium equations, and then we can calculate the force in that member. We do not need to necessarily first calculate the reaction forces. We can, if we actually select a good free body diagram, we can directly find the force in that member. So, next question, is this statically determinate? You know, again, I have two reaction forces here. In total, we have 4 reaction forces. We can only write 3 equilibrium equations. So, how come you guys say that this is statically determinate? Yes.
AB
It's a two-force member. Exactly. So because AB is a two-force member, we know the orientation of that force. So that's only one unknown, and at C we have 2 unknowns. So it means that if I draw a free body diagram like this, I can actually solve this problem. It's not a big deal. So I'm gonna draw the free body diagram of member BC. I'm gonna isolate the member BC from surrounding. This is B, this is C, and here I'm going to have reaction forces at C, so Cx and Cy. And for member AB, I'm going to assume that member AB is under, it's a two-force, definitely a two-force member. Why AB is a two-force member? Why BC is not a two-force member? What is the difference between AB and BC that I call BC, AB a two-force member, but not BC? Yes?
There are only forces at endpoints.
Exactly. BC is subjected to a force in the middle as well, so it's not a two-force member. But AB is a two-force member. There is not any forces applied, you know, transversely along the length of the member AB. So it's definitely a two-force member. So I can just feel that AB, when you press this system, AB should be under compression. Intuitively, I can feel that, but I'm not going to use that intuitive feeling. I'm just going to assume that AB is under tension. So I'm going to assume that AB is pulling point B. So that's why I show it with like this. Although definitely this is wrong, but we'll see. That's why we're gonna get a negative answer for FAB. But let's actually complete the free body diagram. So I need to show this force of 2,000. So I'm gonna do that. 2,000 Newton, and I need to show all the length and angles. So these are the length. I can say this is from here to here is 2 meters, from here to here is 2 meters, and also this angle over here is how much? 60 degrees. So I can, so what equilibrium equation do you guys recommend me writing here? Moment about which point? About point C, perfect. So I'm gonna say sigma m about point C is equal to 0. I'm gonna assume that the positive direction is clockwise for this equilibrium equation. So it means that 2,000 Newton is gonna have a negative moment, so it's gonna be negative 2,000 multiplied by the moment arm of 2. And FAB, the horizontal component of FAB does not have any moment about point C, but the vertical component of FAB has, and it's gonna make a negative bending moment according to this assumption. FAB times sine of 60 degrees. What is the moment arm? It's gonna be 4. Could you please use your calculators and tell me how much will be the FAB from here? With the sign. So it will, sign is clearly negative, but what will be the magnitude of this vector? Yes. I got a little bit different. Yes. I got that. Thank you very much. So almost 1,155 with a negative sign, 1,155. And what is going to be the unit? Unit should be Newton because this one 2,000 is in Newton. So this is going to be Newton. What is the meaning of negative sign over here? It means that this assumption was wrong. I assume AB is under tension. It is wrong. AB is actually under compression. So I'm going to just one moment. So I'm going to say this is going to be 1,155 Newton, and I'm going to write in parentheses letter C, which implies on that this is under compression. Yes?
So is there a reason that we should avoid making these assumptions, or are you just doing that to demonstrate the negative?
What, is there any assumption? Is there any reason that what?
So you said that we can see from the system because it's sucking out the specs, we have compression. Is there a reason that we should avoid using that? Or just
No,
demonstrate
you can just use the right, you know, if something feels right, use that, no problem. But if you are hesitating, that's still fine. You can actually assume that it's under tension and you can wait for the answer, mathematical answers. So the force is known. What should I do next? I think you guys agree that I need to calculate the area and then divide the force by that area. So what is the area of member AB? We're talking about this member right now. We're talking about calculation of normal stress in this member AB. So the problem is saying that the diameter of this member AB is 30 millimeters. So it means that it's a circular crossing, it has a circular cross section. So I'm going to actually calculate that area. That area is going to be pi d squared divided by 4, which is how much? 706.9, is that correct? Would you please verify that? Perfect. And the unit is going to be millimeter squared. So I'm going to say the normal stress at any point across the cross section of member AB is going to be equal to the average normal stress on every cross section of AB, and it will be equal to the force in member AB divided by the area of member AB. And from here, I'm going to say that stress or normal stress in member AB is going to be, or sigma AB, this is sigma. Sigma AB is 1,155 Newton divided by 706.9 millimeter squared. So can you guys calculate this? Yes. Thank you so much. 1.634. And the unit clearly is Newton per square millimeter. Could you please tell me what is the other name for this Newton per square millimeter that is very popular in engineering mechanics? No, the name of the unit. It's not PSI, but only you're in the SI system right now. What is that? Look at the previous page. Megapascal, exactly. So it's going to be MPa or megapascal. So MPa, as I mentioned, is a unit that is commonly used for stresses. Then later we're going to discuss the concept of modulus of elasticity. So MPa and GPa are very common units for stresses. MPa is megapascal, GPa is gigapascal. All right. So, any question about this problem? Yes.
In a homework assignment or an exam, do we have to identify that it's megapascals, or can we just leave it meters per millimeter?
Newton per square millimeter is perfectly fine. So it's up to you. There shouldn't be any points reduced because of not writing Newton per square millimeter megapascal. But as you can see, eventually you might automatically do it. Yeah. But only as long as the units are correct, there's not any it's not mandatory. Yes. All right. Any other questions about this specific example? Yes.
Well, member AB, in the bottom left, how do you say that?
It's a good question. So this is actually a statics question. But this is the answer. If whenever a force is pulling an object is tension. Whenever a force is pushing an object is compression. So I assume, and that assumption was wrong, I assume that member AB is pulling point B. That's why I show it with that in that direction. So this is an indication that this is a tension force. But it was wrong. It is actually pushing member point B. Yeah. Yes.
When you say you find the area, why should it be divided by 4?
That's the equation for area of a circle. Pi r squared or pi d squared over 4. The equation for area of a circle with the diameter of d. Does that make sense? So what is the equation for area of a circle with the radius r? Is pi r squared, right? So for diameter, it will be pi d squared over 4. Yes.
So, does AB, is that force being in tension or compression with that stand?
No. Again, it's a good question. The answer is no. As long as it's an actual force, either tension or compression, we can just simply divide it by area. And that will be a normal stress. So normal, we have two types of normal stresses. Tensile stress, compressive stress. This one over here is a compressive stress because it's because of the compression force. So, if there is not any other questions, we can actually go ahead and talk about some examples where we can calculate the shear stress. So, right now, I think you guys, agree with me that we can simply calculate the stress as long as we can assume that the stress is distributed uniformly. So if the stress is distributed uniformly, we can just simply divide the force by area. That's correct for shear stresses as well. So for some cases, for some engineering elements, it is fine to actually assume that the stress is distributed almost uniformly. And if we can make that assumption, we can just simply divide the shear force by the area and calculate the shear stress. So my point is that this equation could be used for some elements. That shear stress is equal to the average shear stress and is equal to shear force divided by area. But where can we use this equation? So experiences, engineering experiences have shown that it's fine to use this equation, for example, for pins and bolts. And we do it, in structural design, we always do that. We always use this assumption that we can actually just, in order to calculate the shear stress, we can just divide the shear force by the area. So we can definitely use this on bolts. But you guys remember from your class of statics that one location that you always have shear force is in beams. Do you guys agree with me? So for beams, we always draw a shear force diagram. So beams are beamed because they are subjected to shear forces along their length. Otherwise, we do not have a beam. We do not have then the equilibrium of the bending moments is not going to be satisfied. So in beams, we have shear force. Can we use this equation for beams as well? The answer is absolutely not. We cannot use this equation that shear stress is equal to shear force divided by area for beams. Why can't we use it? Because as we will clearly show later in this class, the shear stress in beams is not distributed uniformly along the height of the cross section. So I would like to emphasize over here that this does not apply to beams or on beams. Please be careful of that. But it is okay to use it for bolts and pins. For example, let's take a look at these two parts that are connected with this bolt over here. One of the most commonly used joints in engineering systems, especially in machinery systems. Those of you who are from mechanical engineering, I think you see that example in your machine design course. That we have lap joints. There are so many cases that when we want to connect two plates together, for example, let's assume that I would like to connect, this plate and this plate together, and I need, if I use a bolt over here, I can actually connect these two plates together. Then, when the force is applied, the left member is under tension, the right member is under tension, but this bolt in the middle is going to be under shear. Why will this be under shear? Because let's think about the load transfer mechanism. There is a bolt hole in each of these two members on the left and right, and we use a bolt inside. There will be contact between the bolt shank and bolt hole walls. So here I'm going to have a contact between the bolt hole wall and bolt shank, and here I'm going to have another contact between the bolt hole wall and the bolt shank. So, you know, I can actually isolate the top part of this bolt and draw the free body diagram of the bolt on the top part here. So I'm gonna have bolt head, bolt shank, and this is the cut surface. So here, I know that there is a force that is applied from the bolt hole wall of the left part to the bolt shank over here. Can you guys tell me, what should I use over here in order to satisfy the equilibrium for this free body diagram? I need to use a force that is parallel to that top force. So the top force is to the left. I need to show a force to the right. So this is gonna be the force that I need to use over here as the internal force inside the bolt. Can you guys tell me what kind of force is this? It's a shear force because it's parallel to the cross section. So this is, you know, by using a right equilibrium equation, we can prove that we do have shear force in our bolts. And what's gonna be the value? So if this, how much is this force? Can you guys tell me? The part is subjected to F. How much force is applied to the bolt shank? It's gonna be F. Full force is gonna be applied over here. So if that is F, and this is the V or shear force in the cross section, what is the relationship between shear force and F? They're gonna be clearly equal together. So we can say that V is equal to F. We can actually get the same result if we draw the free body diagram of the bottom part. So in the bottom part, assuming that this is the bolt shank and this is the bolt head, and at the bottom part we do have a force that is applied from the right part to the bolt shank, and in order to satisfy the equilibrium we need to have a shear force. And because this is V, V should equal, because this is F, V should be equal to F. So V is equal to F. But does V always be equal to F in these kind of connections, in these kind of joints? The answer is no. It depends on the number of the shear surfaces. For example, if you look at what we have on the right side, you know, the connection is a little bit different. So we have, it looks like that we have a part that is going through a slot on the left part. So we have this kind of connection, and everything is connected through one single bolt. So in order to identify how much shear force do we have over here, we need to draw the free body diagram properly again. So I'm gonna actually isolate, make it cut, isolate the top part of this bolt, and try to draw the shear force, try to draw the free body diagram. So I'm gonna have a bolt head, I'm gonna have a bolt shank, and this is the cut surface. Can you guys tell me how much is this force that is applied from the left part to the bolt shank? How much is that? Half of it. Half of it. Hopefully, if this is distributed uniformly, we can say half of it goes to top part, half of it goes to the bottom part. We cannot say that the full F is going to top part. So as you guys correctly observed, we can say that it should be around F over 2, or exactly F over 2. In order to, it should be exactly equal to F over 2, because the equilibrium should be eventually satisfied. We need to satisfy the equilibrium of forces and also equilibrium of moment. If we have, you know, if they are not equal, we're gonna have some sort of rotation. But anyway, so it's gonna be F over 2. So if that's F over 2, the shear force, internal shear force inside the bolt this time is not gonna be F, it's gonna be F over 2. We can actually investigate this by drawing the free body diagram, for example, for this bottom part of the bolt as well. So we're gonna have a bolt shank, we're gonna have a bolt head, we're gonna have a force that is applied to the bottom part. Similarly, for the same reason, we can say it's gonna be F over 2. It is applied on this area, which is area of contact between the bolt hole area and the bolt shank, bolt hole wall and bolt shank. So in order to satisfy the equilibrium, we should have a shear force of V that will be again equal to F over 2. If we actually draw the free body diagram of the middle part, we can say this middle part over here. This middle part over here is subjected to the full F. So if you look at this area of contact, the full F is actually applying to this middle part, but we do have two shear surfaces. One shear surface at the top, one shear surface at the bottom. And assuming that these are equal together, and they must be equal together to satisfy the equilibrium of moments. In that case, for this middle free body diagram, again, we can clearly observe that V should be equal to F over 2. So the bottom line is, for the left-hand side scenario, V is equal to F. For the right-hand side scenario, V is equal to F over 2. So I can tell you that this is actually a common feature for bolts in structural connection, mechanical connections, that they are either under single shear or under double shear. So we call this a case of single shear. We call this case a case of double shear, or a bolt under double shear. A bolt under double shear is actually connecting two shear surfaces. A bolt under single shear is connecting one shear surface. So in any problem, if you guys see, or if you guys observe that the problem statement says that your bolt is under double shear, it means that you need to divide your axial force by 2 in order to get the shear force inside that bolt or inside that pin. If the problem is saying that your bolt is under single shear, it means that the shear force inside the bolt is equal to the axial force in the connecting member. What is the example? Same example that we saw in our previous page. Let me just make this more clear. This is point A, this is point C, this is point B. This is 3 meter, this is 2,000. Same exact example that we just solved. And this is the angle. We have a pin support, and these two members are connected together at joint B. The problem is asking that the pin is experiencing double shear. Determine the average shear stress in the pin. What should I do? What do you guys recommend me doing?
Divide the axial force by 2.
So what axial force?
The one that we got from the last.
Exactly. So would you like to add something to that? So exactly. So as you guys see that AB is under compression. We just investigated that in our previous problem. AB is under compression, under an axial force of compression. So it is under compression. It's compressing the pin at point A, but pin A is under double shear. So we just need to divide that compression or compressive force by 2. That will be the amount of shear force in that pin. So I'm going to say that the shear force inside the pin A, or shear force in this pin over here, you just highlight that. We are trying to calculate the shear force here. And the diameter of this pin is given to us. So first we would like to calculate the shear force in that pin, and then calculate its area, and then divide the shear force by the area, because I mentioned that we can use this equation for pins. So the shear force inside the pin because it is actually under double shear, is equal to the force in member AB divided by 2. So it's going to be 1,155 Newton divided by 2, which is going to be 577 Newton. And the shear stress is going to be equal to the average shear stress for pins. At least we can assume that. So we just need to divide the shear force inside the pin by the area of the pin. So it will be 577. Is this 577 correct? Would you please verify that? Is that right? So it's going to be 577 Newton divided by, thank you very much, divided by the area of the pin. So this time, so someone asked me about the pi d squared over 2, right? So this time I'm going to use pi r squared. So I'm going to use pi times 2.5, which is the radius of the pin, taken to the power of 2. So it's going to be pi r squared, or pi times 2.5 millimeter squared. Could you please calculate this stress? How much is that?
29.5 megapascals.
Thank you very much. I got 29.4. Let's accept either one is fine. So I'm gonna say 29.4 Newton per square millimeter, or as you correctly mentioned, it's gonna be 29.4 megapascal. This is how we can actually calculate shear stress in pins, in some simple elements so far. Of course, in real life, every object in this classroom is subjected to some level of stresses. Your chairs are subjected to stresses. All these walls, column, beams that you do not see them, they are subjected to stresses. But these stresses are not distributed uniformly in reality. But in some members, if some assumptions are satisfied, we can approximately assume that those stresses are distributed uniformly. If we can do that, we can easily calculate. This was one of the examples. So in this pin over here, we just assume that the shear stress is distributed uniformly, and this assumption is correct for all practical purposes. And this is the answer, 29.4 MPa of shear stress. Any question about this example? About double shear, single shear? Is that clear to everyone? Oh, perfect. So we do have, we still have 5 minutes. Let's actually discuss what we have at the top of this page. So again, you guys see a bar, a prismatic bar, subjected to an axial force. So what did we just mention about these kind of members? We just mentioned that at every cross section we do have a normal stress, either tensile stress or compressive stress. This is actually subjected to tension, so we're going to have tensile stress at every cross section. But what is the meaning of cross section? Cross section is a section that is perpendicular to the line of axis of the member. How about if you look at some sections that are not perpendicular to the line of axis of this member? For example, if I actually look at this inclined section with the angle of theta, what do you guys say? On this section, do we have a normal force, do we have a shear force, or do we have both? Clearly we do have both. Why do we have both? Because if we do not have both N and V, the equilibrium is not going to be satisfied. So we need to have both. So we can calculate some non-zero values for both of them, both normal force and shear force. So when we have normal force and shear force, it means that we have associated with the normal force, we have normal stress. Associated with shear force, we have shear stress. Again, if we can assume that these stresses are distributed uniformly, we can just divide the force by the area and calculate the associated stress. So we can calculate the normal component of the force by the area of that area, and calculate normal stress, and divide the shear force by the area of that area, and calculate the shear stress. The only thing that we need to pay attention to over here is that the area is not going to be exactly the area of the cross-section of the member, because this is actually a larger area, it's an inclined area. So we need to actually consider that fact as well. I think I can actually at least try to write the equilibrium equation. So what we need to do, we need to actually use this angle theta and calculate n and v as a function of t, which is the axial force that is applied to this member. If I do that, then I can actually find the values of n and v as a function of t. So I'm going to actually use this free body diagram. But instead of writing sigma f sub x equal to 0 and sigma f sub y equal to 0, I'm going to actually use these two axes, a and b. Can anybody tell me why I'm using a and b, not x and y? Because it lines up with n and v. How come it could be helpful? Exactly. So it will help us a lot. It will save us some calculation. Through one equation, I can find n. Through another equation, I can find v. I do not need to solve for a system of two equations, two unknowns. And I can easily solve for n and v. But let's actually do this in the beginning of our next class. So, is there